Welcome to The Explainer. Today, we're diving headfirst into the fascinating collision between our futuristic dreams of urban air mobility and the rigorous, honestly sometimes brutal, realities of aerospace engineering in India. We've all seen the incredible promises of flying taxis that are going to whisk us right over city traffic. But today, we're looking past the glossy renders and the hype to examine the hardcore science. It's a question you've probably asked yourself while sitting in endless city gridlock, right? Like, when will we actually be able to bypass all this and take our first flying taxi? We see these concepts from companies all over the world, promising a totally stress-free commute through the clouds. But look, there's a massive gap between a cool 3D rendering and an actually certified aircraft safely carrying passengers. So consider today our reality check. Here's the flight plan for today's explainer. We're going to start with the flying taxi dream globally and in India, move into the hardcore engineering of the eVTOL, tackle the massive battery bottleneck, calculate the true costs, look at the legal hurdles with the DGCA, and finally, give you the ultimate verdict. Let's get into it. Section 1. The flying taxi dream. The global race to conquer urban air mobility is well underway. And we've got players everywhere, including Indian innovators, all fighting for a piece of what could seriously be a trillion-dollar market. But first, let's lock in what we're actually talking about here. eVTOL stands for Electric Vertical Takeoff and Landing. And just to be absolutely clear, there's no sci-fi anti-gravity tech happening here. These aircraft use electric propulsion to lift off vertically, kind of like a helicopter. But the really clever part is the transition. A lot of these designs then tilt or shift forward using aerodynamic wings for cruise flight. That wing-based flight is highly efficient and dramatically reduces the massive energy it takes to just hover in the air. If we look at the different approaches being taken right now, you can contrast a global pioneer like EHang with India's own ePlane company. EHang's EH216S is currently pushing pilotless point-to-point flights with a 30-kilometer range and a 620-kilogram maximum takeoff weight. But check out ePlane's targets. They are aiming for a highly versatile 110-kilometer range, hitting speeds of 160 kilometers per hour, and incredibly, doing it all within a super compact 8 by 11 meter footprint designed specifically for really dense Indian cities. It is an extremely ambitious target. Which brings us to Section 2, engineering the eVTO. Making those ambitious numbers a reality requires a literal fight against physics. There's a common misconception that you can just take a powerful electric car motor, strap it onto an airframe, and you're good to go. But do that, and you've basically built a flying brick. An EV car motor is heavy, it relies on automotive cooling, and it's just not optimized for flight. A dedicated aviation motor, on the other hand, that's an entirely different beast. It is relentlessly optimized for the absolute highest power-to-weight ratio possible. Because in aerospace, a motor isn't just about horsepower. It's about how much power you can squeeze out of every single kilogram of system weight. These motors need unique aviation cooling and extreme reliability architectures, which makes them incredibly complex and, of course, really expensive. So, the absolutely crucial point here is weight. Weight is the ultimate enemy. Just look at this number, 200 kilograms. That is the strict payload limit for ePlane's air taxi. To put that into perspective, that equates to exactly 1 pilot and 2 passengers. That's it. You can't just toss in another seat without drastically changing the entire physics calculation of the aircraft. When you're fighting gravity vertically, literally every single gram matters. To shed that weight, engineers are having to use entirely new manufacturing workflows. The process goes straight from 3D CAD design into highly advanced aerodynamic simulations. Then, they use lightweight carbon fiber composite printing or molding before putting it through exhaustive structural testing. This hybrid structure of carbon composites and lightweight aluminum alloys is pretty much the only way you build an airframe strong enough to handle flight, but light enough to actually get off the ground. Section 3. The battery bottleneck. Because even if you build the most perfectly lightweight airframe, you're inevitably going to slam right into the single biggest technological hurdle in the entire industry. It's a fascinating engineering trap called the vicious cycle of electric aviation. Think about it. If you want more range, you have to add a bigger battery, right? But a bigger battery means more weight. More weight means your motors have to work harder to generate more lift. More lift requires more power. More power consumes more energy, which means, you guessed it, you need a larger battery, which just adds even more weight. Breaking out of this cycle requires battery cells with incredibly high energy density. And the thing is, a battery cell's raw energy density is really only half the story. You can't just tape a bunch of cells together and take off. An aviation-grade battery pack requires a complex battery management system, aggressive thermal cooling, rigid structural casing to survive impacts, specialized fire containment, and safety isolation. All of these mandatory safety layers add massive weight to the final pack, which severely eats into your actual flight range. Section 4, calculating the cost. Let's pivot from the science lab over to the accountant's desk, because if the physics are unforgiving, the economics are just as tough. Creating just one single working conceptual prototype requires a staggering financial checklist. We're talking about funding custom carbon composite airframes, sourcing those wildly expensive dedicated aviation motors we talked about, acquiring the inverters, avionics, and flight computers, and then paying for the exhaustive ground and flight testing just to prove the concept actually works in the real world. And we have to clearly separate prototype costs from production costs here. A prototype has a massive price tag because of custom engineering, heavy R&D, and low volume. Now, if these companies can eventually reach mass production, automated assembly and economies of scale will drive the per-unit cost down significantly. But getting from a working prototype to a mass-produced model requires passing the ultimate boss fight: government certification. Which brings us to Section 5, DGCA and certification. This is the legal reality. Flying a prototype over an empty test field is one thing. Getting the Directorate General of Civil Aviation, the DGCA, to legally approve it to carry human beings over a crowded Indian city, that is an entirely different universe of difficulty. And this highlights exactly where we stand right now. Check out this direct quote from current DGCA documentation regarding electric engine and motor requirements. It literally just says, reserved, meaning the regulatory rulebook for electric aviation in India is still being written as we speak. The framework is in its absolute infancy, which means these startup companies are trying to design aircraft to meet safety standards that haven't even been fully finalized yet. It's a huge challenge. To even have a shot at getting that future certification, eVTOLs have to feature multi-layered, redundant safety architectures. They need multiple propulsion units, so if one completely fails, the others can instantly compensate using distributed thrust control. They need obsessive battery thermal monitoring. And crucially, this is where winged eVTOLs really have an edge. If there is a total power loss, an aircraft with wings might offer a controlled glide capability, unlike a pure multicopter drone that would just drop out of the sky. Section 6, the final verdict. Okay, let's pull all of this together and look at the true scientific and economic feasibility of the electric air taxi in India. Let's look at our ultimate feasibility scorecard. Is the core technology feasible? Yes, conceptually it is. But the battery remains a major constraint. The motor cannot just be an off-the-shelf part. It absolutely requires dedicated aviation engineering and certification. That is going to be incredibly difficult, time-consuming, and expensive. So a 50 to 100-kilometer electric flight is scientifically possible, for sure. But bridging the gap between a cool working prototype and a commercial certified reality means solving some massive engineering and regulatory equations. Which leaves us with this final thought for you to chew on. The hype tells us the future is already here, but the engineering tells us we've still got a pretty steep mountain to climb. Is your city's skyline really ready for the grueling reality of electric flight by 2030? It's going to be a fascinating journey to watch unfold, and now you actually understand the real science driving it. Thanks for joining us for this explainer, and definitely keep your eyes on the skies.